Welcome back to my Ultimate Beginner's Guide to Carveco Maker. In this final part of our 4-part series, we'll be exploring the exciting world of toolpathing. Join us as we show you how to set up your toolpaths, preview your CNC routing projects, and send it to your machine. With a solid understanding of toolpathing, you'll be able to turn your designs into reality with ease. As always, this video will be broken up into chapters in the description below for easy referencing. Okay, we're going to start a new model, and I'm just going to use 30 inches wide, 20 inches high, max resolution in inches. Today's video is all about toolpathing. Most of the toolpath functions can be found in the Toolpath tab. There's some in this little section on the toolbar above. If you click toolpaths in the project window over here, all of the functions for toolpathing can be found in the projects box on the right hand side. This is where I would suggest working with all your toolpaths. It's just easier to get to everything. The bar at the top only lists a few of the toolpaths, while the box on the right kind of gives you all of them. The first section is our toolpath operations, where we're going to have things like saving our toolpath, the summary of our toolpath, bit database. We also have our material set up. We can delete our material, and we also can create bridges. I'm going to go over all of this in just a few minutes. The next section down is all of our 2D toolpaths. We have our profiling toolpath, our fluting toolpath, the area clearance, the V-carve, the bevel V-carve, the drilling toolpath, and the inlay toolpath. The next section is our 3D toolpath and a laser toolpath, and the last part is our simulation to simulate all the toolpaths that we're going to do. We're just going to grab a vector from our vector art library, and I'm going to use this shop sign. Not everything is in black and white for an example. We're going to start with a profile toolpath. The profile toolpath is a toolpath that takes any vector and runs a profile along, outside, or inside of that vector. Anything that you want to cut that makes a single cut along a vector, this is your tool. And at the top, you can set the profile for the outside of that vector, the inside of the vector, or to follow along that vector. You have an option for the selected vector, or if you select the default layer, it will select all of the vectors that are on that layer. The allowance allows you to set a distance away from the vector. Normally the bit is going to try to follow right along the outside edge of that vector, but you can set an allowance to give it some space in case you need a little bit more material left when cutting your vector. You can set it to try and do sharp curves. If you uncheck this, it will make one sweeping movement around the corners. Sharp curves takes a little bit longer to machine because the CNC has to change direction. But when you have rounded curves, the cut is going to be much faster, but it is going to round off your curves. Final pass thickness and final pass allowance to designate how much material is going to be left for the last pass of your bit. Let's say you have a 1/2 inch piece of material and you're cutting a 1/4 inch at a time. It's going to take 2 passes to get to the bottom of that material. If you set a final pass, it will recalculate so that it makes a final pass at that depth. So if we put final pass thickness 0.01, it would make a pass at 0.25, then it would make a pass at 0.24, and then finally make a third pass at 0.01. The same thing with the final pass allowance, allows that last pass to be either closer or further away from the vector. I often use a negative allowance in order for the final pass to be very close to the vector. That will allow it to skim the wall again and clean things up. That's just a little trick. Your cutting depth is where it's going to start. Normally your starting depth is the top of the material or at 0 inches. However, there are times where you may need to start your cut further down. Let's say you've already removed material from a different cut and your new starting depth needs to be slightly lower. This is where you would set your starting depth. Your finishing depth is the depth of this cut. So if we had a 1/2 inch piece of material and we only want to cut a 1/4 inch into it, we would put a 1/4 inch. If we want to cut this piece out and cut all the way through the material, we would put this at a 1/2 inch. If you have already set up your material before you open this toolpath, it will automatically select the max depth of your material. At the bottom of every toolpath is the material setup, so this button for defining your material can be found at the bottom of every toolpath. Let's go over that real quick. If I click to define my material, it brings up the material setup box. The top box is our model thickness, and since this is just a vector, there's no model thickness to this. And then the next box is our material thickness. If we had a 1/2 inch piece of material, we would put in a 1/2 inch here. The material Z0 is where you're going to probe your material. If you probe from your wasteboard, then you would want to have this set at the bottom. If you probe the top of the material, you want to have your material Z0 at the top. The model position in material is where in the material that this particular cut is going to happen. We'll go over this a little bit more in a little bit when we do the 3D toolpath. Right now we're just going to set it up for a 1/2 inch material, and that defines it at the bottom. The box above it is our Safe Z and our Home Z. Home Z is where the router or spindle is going to return at the start and the end of every toolpath. So when you press start, the Home Z is where the router is going to move to start the toolpath, and when the toolpath is complete, the Home Z is where the router is going to retract to. It's a good idea to leave enough room for bit changes in between your toolpath and to clear your material and any clamps or anything that you may have. Your Safe Z is where the router or spindle is going to retract in between moves across the material inside the cut itself. So while the cut is happening and the router needs to change position, it will retract to this height and move across the material to start the next position. Generally, you want to have this large enough to clear any kind of clamps or anything that may be on top of your material. However, this adds to machining time. So if you use a really small, like sometimes I'll use a 0.05, and this will allow the bit to rise just 0.05 above the material and travel across it. This will reduce machining time. However, if your material is uneven, it can scrape or run across the top of the material. You need to be careful not to use a too small of a number here. And if you have clamps or something that you're using on top of the material, you want this number large enough so that your router is retracting over the top of those and not running into them. You also can set a home X and Y offset. Generally, if you want to keep this where you probed 0, you just leave it at 0, but you can put an offset for X and Y. Going back up to the top, the next section down is our tool selection, and if we click to select this, it's going to open up our tool database, which was also found right here. The tool database is going to open up to select the desired bit. Now I have a section called My Tools that I have created, and normally the software will come with the metric, inch, I believe it comes with this jewelry tools, legacy woodworking. I've downloaded some of the manufacturers' tool databases and imported them with the import button down here. For instance, this is the Jenny bits from Cadence Manufacturing, and it gives you some starting settings to work with. Do note that these settings are not machine or material specific, and so the spindle speed, the feed rate, and the plunge rate will not be what you want to use. You need to use a chip load chart to dial in those feed rates depending on what type of material you have. I have a whole video on that subject that I will link above. It's very important to understand what chip load is and how that works, so I highly recommend checking that out. To create your own tool group, all you need to do is go up here to Tools and Groups and add a group, and then the same thing with adding tools. You can create your own library of your own bits. I have most of my common tapered ball nose, my V-bits, my end mills and ball noses, and all you need to do is add a tool and set up your own bits. For this profile pass, we're going to actually select an end mill, and let's use a 1/4 inch upcut end mill. Once you select your tool, you can push this little arrow on the corner of the bar there, and it will drop down those settings. And then once you dial in your feed rate and plunge rate, you can enter that information here for each cut, and it won't change it in the database. You can have a setting in the database that's a common setting, and then for each cut, you can dial in the speed that you're going to want to use depending on what kind of material you're cutting and the machine that you're using. It gives you an option for for the cutting direction, climb or conventional. The cutting direction is moving in the direction that the spindle is spinning. So if you are moving in the same direction that the spindle is spinning, that would be the climb. If you're moving against the direction that the spindle is spinning, that would be conventional. Climb is usually a better chip remover, and so you can go faster when using the climbing cut. However, conventional cut can give you a better finish, but normally with only very, very small material being removed. If you're removing a lot of material, the conventional cut doesn't remove chips as well, and so it can drastically affect your chip load and can slow things down. The next step down is our add lead in and lead out moves. Normally when you start a profile cut, the router is going to move to the start position, and the start position is designated by this green dot. It's not a good idea to start your cut in a corner. I suggest if you are going to set up toolpathing and you have a start position in a corner, it's a good idea to move it. To move the start position, we just need to create a new starting node. If we press N to go to our node editor, we're going to press I to insert a node, and P to create a starting node. Then if I close my node editor, I've moved my starting node to this little flat spot. I'm going to go ahead and press calculate to show this. Normally the router is going to move over and plunge down and make each cut to cut this out. We told it that it had a 1/2 inch material down here, and we're cutting a finishing depth of 0.5. Our step down was 0.125, so it's going to step down 0.125 until it gets to the bottom. We set a final pass thickness of 0.01, so you can see that final pass thickness of 0.01 that it's going to cut at the bottom. If you do your profile cut using this method, sometimes you can get what's called a dwell mark or a plunge mark. A dwell mark or a plunge mark is where the router is plunging into the wood, and because the forces are different from it moving sideways, it creates a little divot inside your wood. One of the ways of preventing dwell marks is to use a lead in, lead out move. Now we're going to set this lead in, lead out move to 1/2 inch, and I'm just going to use this for a demonstration. We have it set to linear, which is a straight line, and we're going to angle in and angle out at 45 degrees. I'm going to just hit recalculate so I can show this. We want to turn off automatic positioning, because automatic positioning tries to pick the best spot to lead in and lead out, and because it's off the material, it thinks that this is a good spot for it. But if we want it to start on our start node, we would have to unclick automatic positioning, and then it's going to start on our start node. Now this lead in and lead out move is going to come out away from the material, plunge in, and then move in at an angle, then change position, start the cut. I would never really use this because of the angular movement that it has to make the cut. You can still get dwell marks using an angled entry. It's better to use a circular arc, and let's say our distance is of 1/2 inch, so our arc needs to be larger than 1/2 inch. If we had a 3/4 inch arc, let's recalculate that. This allows to have a smooth entry into the wood, and the lead in, lead out moves move into the wood and they come out of the wood in a smooth motion. This is one of the better techniques to removing dwell marks. The other way to do this is to add ramping moves, and ramping moves are entering the wood at an angle from the top down. Instead of entering the wood from the side, we're going to enter the wood from the top down at a different angle. And you can pick the spiral ramping move where it will spiral down into the wood. There is the zigzag where it will create these angles, and you can set the angle, or it will create a smooth ramp where it just takes one move into the wood at a smooth angle. The lower the angle or the smoother it can enter the wood, the better. The higher the angle of degree, the more forces that it takes to enter the wood, and so it's a little less efficient. Ideally you would have below 20%. I like to use 10%. I found this as a good ramping angle, and I often use the smooth or the spiral ramping as I find these patterns to give a better finish when available. I mainly use the smooth ramping as I find this to be the quickest and the most easiest way to ramp in. And if we recalculate, you can now see that at every move, instead of coming straight down, the router is going to get to these lines at an angle. And because the cutting forces are not as great, you're less likely to have dwell marks. Ramping is the go-to method for reducing cutting stresses at the start of your cut. And I highly recommend adding ramping where the bit's entering the wood with 100%. So like the first cut where the bit's going to plunge down into the wood, you want ramping. If it's making side profile cuts where it's just cutting the step over, then the ramping is not nearly as important. The next box down is our bridges. And what a bridge is another word for a tab. It's material that is left over to help hold your piece in. You can add a constant number of tabs. You can have it space them based on a measurement, and you also can select constant spacing. I often use constant number just because it's easier to set the tabs how you want them. You want to put in a length and a thickness of these tabs. I like to use 1/4 inch. The next box is where you set between 3D bridges and 2D bridges. 2D bridges are stronger, but 3D bridges machine faster. 2D bridges are square, so the router has to rise up to cut over the top of it, while the 3D bridge, the router continues the movement as it's moving over the bridge. That's the difference. You can check this to have it to add a bridge on the start point, where it will try and add a bridge where the router is going to be ramping into. This can help put your start point on top of a tab, and if you get dwell marks and you have a tab in the same spot, you'll be sanding that spot anyway, and so it's just a good way to have all those different things line up at the same spot. If we press add, it's going to add these tabs around the border of our profile. If we click the edit bridges, we can select these bridges and move them where we want them, and then when we press calculate, it's going to create these bridges, or it's going to leave this material that's going to help hold our piece in. Now at the end of every calculated toolpath, we can now simulate this toolpath, and at the bottom of this profile is all of our options for this profile. We can save this toolpath and send it to our machine. We can delete it. We can edit the toolpath and rename it. You can also rename it here. This calculate toolpath is the same as this button here. You can make copies or duplicates of this toolpath. The toolpath summary gives you a basic summary of your toolpath, including estimated machine time. Now the estimated machine time is based on the rapid rate and the time scale factor. This may not actually be that accurate depending on what this is set to, and this has a lot to do with your machine. But when you load the file onto your machine, the machine's going to tell you how much time that it's going to take to make that cut. So once you figure out what that time is on your machine, you can come back here and play around with this to get this to match. And then that will be the same for every project. We have two buttons here for simulating this toolpath. This gives you a control bar where you can simulate the toolpath out a step at a time, where it just shows you the toolpath slowly. You can speed it up. You can also just simulate the toolpath completely by pressing this button, and it'll run it all the way out. And you can see that our profile cut has cut and left those bridges in place. And that's our profile cut. If we drop this bar down, we still have our profile toolpath here. We can create all the toolpaths for this project and save them all at once, or you can save them one at a time. I'll go into this in just a few minutes. For the simulation, when you click on the simulation, you have some options here. This button allows you to simulate all the toolpaths again. This button clears or resets the simulation. You can delete the simulation, and this button, it allows you to delete the waste material so that you can see what just your project looks like. Now, because I have tabs connecting my project to the waste material, if I try to delete the waste material, it's going to just delete the project. If I didn't have the tabs there, I could delete this part, and you would be left with this. You also can change what the material looks like. You have all kinds of different choices in here to change it to like light oak, a medium oak. The H and the V is the pattern, whether it's running horizontal or vertically. So that's the wood grain. The depth of color and the dynamic display level of detail. The depth of color is when you have something carved in here, it will shade in the darker parts. I'll show that in just a few minutes. For now, let's delete our toolpath. We're going to bring our vectors back up. And for now, I'm going to turn off this toolpath so that we don't get that toolpath vector in our project. Notice it keeps the bridges in there. That helps remind you where those are going to be. We go back up to toolpaths. The next toolpath I wanted to go over is our area clearance toolpath. And the way the area clearance toolpath works is it clears inside of any selected vector or selected vectors. So I can select one vector, say the inside of this, and it would clear all of the material inside of this at whatever given depth that I wanted to give it. So if I wanted to clear this out, we have our 1/2 inch piece of material. Once you set up your material, all the following toolpaths will retain your home Z, your safe Z, and your material setup. So you don't have to reset that up for every toolpath that follows once you set it up the first time. So if we want to make this pocket at 1/4 inch, because our material is at 1/2 inch, we could put in 1/4 inch here. Again, our start depth is where on the wood it's going to start. Our allowance is how closely the bit is going to follow the vectors. We have a final tool allowance, and I'll explain this in a minute. And then our tolerance. Our tolerance is how closely the cutting pattern follows inside the vectors. And while you do want this small, 0.001, I don't suggest going anything smaller than that because it takes a lot of computing power, and this can lock up your computer. It also can add more steps and create longer cutting time. The next box down is our tool list, and if we click add tool, it's going to give us our tool database again, and we're going to select the tools that we're going to use to clear this area. Now, unlike the profile pass, you can add more than one tool. I can add this 1/4 inch upcut. I can add a 1/8 upcut. And what this does is this allows you to pocket using different size bits to get into tight areas. Right now we're just pocketing inside this large area, but we could pocket inside this large area and around the lettering. So if we select the lettering, now let's unselect outside profile. Now we're going to pocket everything from the wall of the inside of this plaque to the letters. And because the spacing inside of these letters is really small, we're going to need a small bit to get inside of there. So that 2D area clearance will machine everything that the 1/4 inch can reach, and then it will set up a second toolpath that will allow the 1/8 inch upcut to cut everything that it missed. Again, we have our different settings for each bit and the feed rate, which you want to adjust for the material that you're using and your machine type, so you can adjust your feed rate for each one of these bits. And for the area clearance, we also have a tool strategy or a clearance strategy. We have the roster and the offset toolpath. The roster toolpath is a simple toolpath that goes left to right and clears the material moving back and forth across the material. You can set a different angle. I like to use a 45-degree angle for my roster cuts. Often if you run a 0 angle or 0 degrees with a roster cut, because your material is laying across your work bed, you may be cutting with the grain. This can sometimes create splintering and chip outs. It's better to cut across the grain, and using a 45-degree angle ensures that you're cutting across the grain in both directions. The offset toolpath is a little different. It actually takes into account everything that is trying to be cut, and it will try and go around each part, starting from either the inside or starting from the outside and spiral in. So it will spiral in or spiral out around each of the objects. You can set it for climb or conventional. I recommend climb. And you can have it start on the inside or the outside. This has a lot to do with where the details are at. Often, if I have a lot of details on the inside of my project, I will start on the outside. And if I have an open spot on the inside of my project, I'll start on the inside. I generally try to create my starting place away from all of my details that are in my project. We have our ramping moves, the same as we did in our profile, and then our other options are also still saved. If we press calculate, you can see by using our offset toolpath how it went around and offset. Now if I use the simulation, we have that depth of color checked, and that's why the background is black. If we uncheck that and press apply, we can get rid of that depth of color. The depth of color shows you everything that you carved. So it's a good way to see what we missed. We did not get the R, the O, and it missed a lot of the detail. And this is because the bit was too large. Even the 1/8 bit was too large to get into these areas. So if we delete our simulation, let's turn our vectors back on, and let's go back and we're going to add another bit. This time I'm going to add the 1/32 taper ball nose. We're going to use the offset. When you click on each one of these, you can set each bit has its own clearance strategy. So you can use different clearance strategy. We could take the 1-inch upcut, have it use the roster, and we could add ramping to our 1/4 inch. Then we could come back with our 1/8 that we don't need ramping and run an offset toolpath starting from the outside. And then we can come back with our 1/32 toolpath offset. We'll start from the inside and we don't need ramping. And now let's calculate and let's simulate. Now we got a little bit more stuff, but we still didn't get all of those details, and that's because the bit is still not small enough to get into those places. There's some really tiny detail. And sometimes you need really tiny bits to get into these really tiny detailed spots. Let's clear our simulation, and we could continue to add smaller bits. If I just remove that, if I add, go to a Mana V-bit 1/4 inch shank. They have a 18-degree carving liner. It's a really small bit. And let's calculate that. And now if we simulate, that carving liner got inside the letters. And you can add as many bits on here as you need to get down to the areas that you want. And it's a really powerful tool because the smaller bits do not have to recut what the bigger bits had already cut. And that's our area clearance toolpath. The next toolpath I wanted to show you is the V-Carve toolpath. And the V-Carve toolpath allows you to carve using a V-bit or a taper ball nose bit. We're going to select a 60-degree V-bit. We have our selected vectors. Our start depth is the depth from the top of the material. We have our carving tool with our feed rate and settings that we can adjust here. This button below is the width and depth of cut information. In V-bit carving, the bit is going to go in the middle of the vectors, and it goes as deep as it needs to go to reach the outer edges of that vector. The larger the degree of the V-bit, or the wider the V-bit is, the less deep it needs to go to reach those outer edges. The narrower the bit is, the deeper it needs to go to reach the outer edges. So with the 60-degree V-bit, if I press the refresh button, this is going to give me the information of how deep bit needs to go to reach those edges. And it says that my maximum depth is 0.55 inches. If I were to calculate this, it would cut through the material because it needs to go down 0.55 inches to reach both sides of this vector. If I select a 90-degree V-bit, now I'm going to press refresh, and you can see that the 90-degree bit only needs to go 0.31 inches down to reach the edges of these vectors. So if I calculate this, and let's go ahead and run our simulation, then the V-bit went down and carved in one pass the depth that it needed to reach all these vectors. Now this time, let's go back to that 60 degree. Let's calculate again. This toolpath will cut through the material base. So if I simulate it, you can see that that toolpath would have cut through material entirely. Now what we can do is limit the depth of that cut. Let's say we only want the bit to go down the entire thing 0.25, so we can limit it. We can say 1/4 inch, and now when we calculate, let's go back to our simulation. Now you can see the bit went down to 1/4 inch to its maximum depth, but it still needed to get over to the other line, so it stepped over until it got to the other line, and it left all these little grooves at the bottom. This is where our roughing tool comes in. And if we picked a roughing tool, I'm going to pick, let's go to an end mill, and I'm just going to pick a 1/8 end mill. Select this, and what this is going to do is the roughing tool will attempt to cut any of the material that the V-bit can't reach in one pass. So if we calculate now, you can see that the 1/8 bit came down, cut this area in this pocket because the V-bit couldn't reach it. the 1/8 bit is too large to reach these areas inside the lettering. So you actually would want a smaller bit to do that for this example. The better way to do it would be to select the 90-degree V-bit, which can cut everything in. And if I calculate this, our V-bit can get it almost everything in one cut. But because we limited the depth to 0.25 and the V-bit can cut to 0.31, it still was restricted and stepped over. And so the 1/8 upcut end mill had this one spot that it was able to cut. If we were to uncheck the limit tool maximum depth and we press calculate now, it's going to tell me that there's nothing for the 1/8 end mill roughing to cut, which we can just press OK and it will skip over that. And if we go to our simulation of our V-bit carving and simulate that out, you can see that cut it all in one smooth cut, and it looks much better. What you can do sometimes is cut, say, the middle part out with a 90-degree and then come back and cut the little letters out with the 60-degree and get different depths for each one of these letters. Breaking the project up into the different tool paths that work best for what you're trying to do is the best way to tackle a large project with different sizes. You can do as many tool paths on a project as you want. You can do as many V-bit carvings, as many profile passes, whatever your project calls for. If we go to our simulation and we click the simulate all toolpaths, this will simulate all the toolpaths that we have created. So we created a pocket toolpath that gave us this pocket inside of here, created a profile toolpath that ran along the outside here, and we created a V-bit toolpath, two different ones, one that got the black and white and one that got not everything is in. I'm going to show you this, what it actually did. This is pretty interesting. It actually pocketed those letters and then V-bit carved them on top. You probably would not have wanted to do a V-bit carving on top of raised lettering. I was just basically showing you how to do that, but you can get the concept. And there's some interesting things that you can do by stacking these different kinds of toolpaths. Go back to our toolpaths. I want to show you how to send this project to your machine. So if we had this project and we wanted to send this out to our machine, we would click our Save Toolpath, and this is going to bring up all the toolpaths from our project. This box is all the toolpaths that you're going to save, and these are the calculated toolpaths. You can move these toolpaths over to this box over here. If you want to separate certain toolpaths, let's say you only wanted these 3 toolpaths to send to the machine and you really didn't want to send these 3 toolpaths, you can separate which toolpaths you're including in your save. You also can click this box to save toolpaths to separate files. I would suggest doing this for every single toolpath as saving it as a separate file. If you run each toolpath as a separate file, at the end of each toolpath, the machine's going to return back to its starting spot and you'll be able to probe and change your bit for the next toolpath. If you save these toolpaths together, it's going to save them as one G-code file and it will save them combined. So what's going to happen is when you run this, it's going to try and run the profile, then the area clearance, then the V-bit right behind each other. It will pause in between each, but as one file, you won't have the option to reprobe or move the spindle on most machines. It's just a better practice for most desktop hobbyists, CNCers, to save your toolpath as a separate file. Append toolpath details to file names. This checkbox basically adds all of this detail, what the tool actually is, to the name of the toolpath. If you didn't go back and say what all these different area clearances were, then they may all just say area clearance. If you click append toolpath details, when we save it, it's going to add all this information, which is helpful when you load it into your machine to know what bits are being used for what toolpath. This box allows you to add the home move to the end of all your files, and this box opens the toolpath folder after saving. Your spool directory is where it's going to save the toolpath, and you can change that with this button here. You'll want a file name for your project that is going to be loaded onto your machine. The next box is your machine file format, or the type of machine that you have. I'm using the Onefinity CNC. The Onefinity CNC has a couple of different post processors you can use. The post processor is the code that is designed for your machine. So you want to make sure that you're using the right post processor for your machine. So if I save all of these, it tells me I've saved my toolpaths. And now I have all these different toolpaths saved that I can load onto my machine. Now I would just put these on a thumb drive or connect through your network and load these files onto your machine for cutting. And each one of these is the different toolpath. That's how you load and save and send files to your machine. And now we're going to look at the bevel carving. Bevel carving is very similar to V carving, except bevel carving is the opposite of V carving. Instead of carving downwards, you're carving the bevel upwards. We're going to select our lettering for the bevel carving, and I'm going to select the Carve tool as the 90-degree V bit. And we do not want to cut all the way through our material. It says 0.5. We're only going to go 0.25. And we want our wall height. Let's also set that to 0.125 or 1/8 of an inch. If we click center line, just like the V-bit gave us our max depth of cutting down, the center line gives us our max height of 0.638. And what that means is in order to make this a perfect bevel on top, it needs 0.638 inches to form each one of those. If I were to calculate, we forgot a profiling tool. We're going to add a profiling tool, and this is to go around the letters. And I'm going to select something small, the 1/16 taper ball nose. You can set it to climb or conventional. You can change the feed rate if you need to. Now it's saying that there's not enough height to complete the whole bevel. That's because my material is not deep enough or thick enough for the entire function for the size that these vectors are at. If we were to simulate this, you can see that it's given us this beveled carving that has some letters standing proud. Now what you would want to do after this is to run a pocketing toolpath around all the letters to cut away the material away from the letters. And that would give you this beveled raised look. Let's close this, close our simulation, open our toolpaths back up. And let's do that. Let's do the area clearance again. We're going to use the 1/8 down cut, and our finished depth is 0.25. Let's use offset and let's calculate that. Now if I go to my toolpaths and let's bring up a simulation, let's simulate all the toolpaths. You can see that now that we've done that area clearance, we have our beveled raised letters, which is another way to do that raised letters with a bevel look. This toolpath is overlooked by a lot of people. They probably don't really understand how the bevel toolpath works, but it can give you some really neat and interesting designs. And I'm just going to delete this. I'm going to go over the Fluting Toolpath. In order to show the Fluting Toolpath, I'm going to draw a vector. What a Fluting Toolpath is a design ramped cut. I went over ramping in the profile toolpath about how the bit can enter at an angle. A fluting toolpath is where the entire vector is set up to cut it at an angle. The direction of the cut is denoted by this little arrow that's in the middle of the line. You can reverse the direction by clicking the reverse direction box up at the top, and it will change the direction that the flute's going to go. The final pass thickness is how much material is going to be left for the final pass to cut. So if you want like a 0.01 final pass thickness, the bit will make as many passes as it needs and then do a 0.01 cut on its final pass. Your start depth and your finish depth. For this, we're going to use a finish depth of 0.25. Our material is still set up at a 1/2 inch. For the fluting tool, I'm going to use a ball nose, and we're just going to pick the 1/4 inch ball nose to show this. You have two options: specify start and end profile, which is the start and end of this vector. You can also use a Z control vector, which is another vector that's used to shape this vector. When we specify our start and end profile, linear is a straight line. We can also set this at a curve. If I put this at 100%, we're going to set the end flute to none. Step down is just going to be a scaled strategy. If I press calculate, and I'm going to simulate this. Okay, and once we simulate that out, you can see that it started here and ended at our 0.25 over here, creating this gradual flute. Now I'm going to change the fluting to 50%. So if I change that to 50%, what that did is the bit went halfway to the 0.25. If I change this to 0.25, 25%, let's calculate, then it only went 25% of the distance and then went the full 0.25 depth. The lower this number, 10%, it would only move 10% and then go the full depth. At 75, it would move 75% and then get to the full depth. If we put this back on 25, and now let's add an in flute, also of 25. Now it will go down 25%, run the full length, and then exit with the 25%. And that's how you set a start flute and an end flute. I have these as linear or straight. You can also create a curve. If we simulate that, and it'll create a curved bottom. You can create a custom curve by designating the degrees. You also have a step down strategy, and this is how it steps over to make each one of these cuts. You can have it step over or extend above the start and cut down through the material, or you can have it all scale from the same spot, just depending on how you want to do that. That's how the fluting tool works. I'm going to show you the drilling tool path. You're going to pick a tool that you want to drill with. I normally just use end mills. Use an 1/8 inch upcut end mill, and you just select the circular vector that you want. You can set a tolerance. You can have it do a plunge move. You can set it to peck drilling. Peck drilling is where the bit goes into the wood and then retracts a certain distance. It's useful for bringing chips to the surface. So you can set a retraction distance and it will go down and peck at the hole and bring the chips to the surface and then go back down. Or you can have it circle down and create the drill path. You hit calculate now. We had our finished depth set at 0.5, so it drilled all the way through the material. Our last tool path is our 3D tool path. So we're going to need a 3D object to carve for the 3D tool path. I'm going to open up my Relief clip art library, and we're just going to grab the beagle, and I'm going to set him to a 0.25 depth, and let's paste it down. We have our beagle pasted down. We're going to do a 3D machine relief of that. Now when I opened up the 3D relief, it said that the model is outside of our current defined material block. Would you like to adjust your current material block? If we press yes, it opens up our material setup. We can see that our material is 0.5 inches thick. Our model is 0.24992 inches thick. This is where the positioning in material comes into play. Right now we're leaving about a 1/4 inch of material on the bottom, and we're carving this from the top. We can move this model into our material, and this will cut this material off before it starts creating the model. So let's say we only wanted to leave 1/8 of an inch down here at the bottom, 0.125, and we're going to leave this 0.125 at the top, and we're going to move our model right in the middle of our material. We'll click OK, and our model is inside of our material. For the 3D machine relief, we have a couple of different options at the top. The first one is whole relief, and what whole relief is going to do is machine the entire piece, including the waste material and everything. It's going to machine it down to our material depth, to that 125. So if we machine the entire relief, it's going to machine everything down the base to 1.125, which is what the material we left at the bottom of our model, and it's going to carve out our model. We can select automatic boundary, and what automatic boundary is going to do, it's going to try and create a boundary around the outside edge of your model. Now you can tell it how far of an offset you want that boundary to be. And what this does is this allows you to carve your model without carving all of the waste material, which could really save a lot of time. You can designate it to carve inside or outside that boundary. Since it's an automatic boundary, you're almost always going to be using inside vector. I like to create my offset the size of the bit that I plan to do my roughing with. So if I'm using a 1/4 inch bit to rough, I like to have my offset as 1/4 inch, but you can change this to whatever you want. We have a finishing bit and a roughing bit. The roughing bit's going to carve out most of the material but leave a small amount for the finishing bit to cut. Let's pick our roughing bit first, and we're just going to pick a 1/4 inch downcut end mill. And we have some tool strategies. Of course, we can change our speeds and feeds depending on our material. We have our roster or offset tool strategies for our roughing. For this, I'm just going to use the roster at a 45-degree angle. In the 3D, it allows you to run a profile pass. You can run the profile pass before, during, or after the clearance pass. I like to do my profile pass afterwards. After it clears the roughing for your model, it will go back around and do a profile pass at the end. You can set the cutting direction for climb, conventional, or both directions. Both directions will definitely be the fastest. However, if you're looking for a particular finish, you may want to change that to climb or to conventional. We have a tolerance, just like our other toolpaths, but we also have an allowance. The allowance is how much material is going to be left for the finishing bit. So we're going to leave 0.02 inches of material for the finishing bit. Underneath that is our Z slices, and this is set to automatic. This says it's going to take 3 slices, and each slice is 0.118. You can set up how you want the slices to carve out. I normally just leave this on automatic. We can add our ramping moves to our 1/4 inch bit. When you add ramping moves to your roughing bit, it's also going to add them to your finishing bit. And this does add carving time. It is a good idea to ramp your roughing bit though. Our safe Z and home Z is all set. Our material thickness is set. Let's pick our finishing bit. The smaller the bit, the more detail you can get, however, at the expense of cutting time. The larger bit that you can use to get the detail, the faster the cut will be. I like to start with a large bit and test to see how much detail I'm getting before stepping down to a smaller bit, because if I can get everything with a 1/8 bit, it's going to be half the cutting time as a 1/16 bit. So let's select our 1/8 tapered ball nose, and for our tool clearance strategy, we only have our rasta available. We have an option to do multiple Z passes. I do not suggest checking this. You can have it do multiple passes. This just adds to your cutting time and will not provide much of a better finish. Okay, we're ready to calculate the toolpath. And first it's going to create our automatic boundary, and then it's going to calculate the area clearance toolpath and then the finishing toolpath. Now I got this box that says that these plunges cannot be ramped, and this is all in the finishing path. Do you still want to ramp this toolpath? You just select yes. And then if we simulate our toolpath, you can see that we've got our 3D dog cut out. Now this model does not have very good detail. It is not very 3D like, and we only cut out a 1/4 inch around the model. Let's close this simulation. I'm going to go back up here to automatic boundary and select whole relief again. One thing I wanted to point out is when you're doing the entire relief, instead of having the automatic boundary, in the finishing options, you get a few more clearance strategies. You get the rasta X and Y clearance strategy, the spiral clearance strategy, and the spiral in a box clearance strategy. The rasta X and Y is similar to the raster toolpath, except it goes back and forth horizontally and vertically. So it adds another run of vertical passes on top of the horizontal passes. This toolpath strategy can give you a really nice finish, but it takes a really long time to. The spiral toolpath is a really great toolpath because the toolpath is always moving against the grain in a spiral pattern. It's one of the more desirable toolpaths. However, the standard spiral toolpath, when it reaches the edge, continues to spiral out. And so there's a lot of wasted movement that can come when using just the pure spiral toolpath. The little more advanced is the spiral in a box. Lets the computer put constraints on the outside edges of the material, and it will only run that spiral inside that box. Spiral in a box is the best finishing strategy that is offered in Carveco Maker. However, you can only use it in the whole relief carving. If you select automatic boundary, you only get the Rasta Classic. You can also have a selected vector, which also is only going to give you the Rasta Classic. And what selected vector is good for is if you want to section off portions of your carving that you want to carve. I could create a selected vector that was just a box around this, and then we could carve everything inside that box. instead of the boundary that just went around the border. It's just another way to do this. Another thing that you can use selected vectors for is to create different areas that you want to use different bits with. So if I wanted to just carve just the face, let's create a box. I could create one 3D toolpath with everything using the 1A tool bit inside that big selected vector. And then I could create a second toolpath with selected vector, just the small vector, and we'll use a 1/32 bit. And we're not going to do a roughing pass because we did the roughing pass with this machine relief cut, and I don't need ramping, so we can undo that. And now if I press calculate, it will run that 1/32 as a finishing pass in that square. And then if I simulate, we cut all the stuff outside that box with the 1/8 bit, and everything inside of it we went back and got some more detail with our 1/32 using a second machine relief. That's another trick to get better detail in small spots where you don't want to machine the entire relief. One thing I wanted to show real quick is now that we have our machined relief, let's say we wanted to cut this dog out. We go to Vector, Create Relief Boundary, and we're going to create a boundary around our relief. Get to show our vectors. Let's get rid of this box. Let's get rid of this box. Go back to our toolpaths. We can select that boundary and create a profile toolpath outside selected vectors. Turn off this final pass. We're going to cut it out. We're going to use a profiling toolpath, and we're going to use a 1/8 upcut end mill. Cut it out. I'm going to add ramping. Use a smooth ramp, and I want to add bridges, so we're going to add those. And calculate. Now if I go back to my toolpaths and let's simulate all my toolpaths, I now have that 3D dog where I can cut it out. And that's how you can cut out your 3D reliefs even though you don't carve them all the way through the material. If you stuck around this long and thought this was valuable, please subscribe to our channel. Give us a like and share this with someone. If you have any questions, please leave them in the comments below. Thanks guys, have a good one.